So hi everyone. Um, I was actually going to do this video with like LaTeX type notes and all, but then I had some problems with my microphone, so I realized that maybe the good old way is the best way. So this is basically like some basics of quantum mechanics. Yeah, so we're going to start off with something really basic, the Schrodinger equation. Um, so the Schrodinger equation is basically this equation, iota h bar and then partial psi upon partial t is equal to h hat psi. Now what is h hat? H hat is an operator. By the way, I think you all know like a bit of wave mechanics and all, right? So psi is just a wave function, and this wave function represents particles. Yes, that's sort of weird, but like wave particle duality says that yeah, every particle is a wave as well, right? So there's this guy who like came up with the wavelength of these waves and all that. So let's not get into all that. But yeah, so this equation basically governs almost all of quantum mechanics. And the worst part is that this is actually a postulate. So yeah, this wave equation is just a guess, really. Like there is no basis for this. Like it can't be derived or proved or anything like that. This is one of the postulates of quantum mechanics, right? And there's another very important postulate as well, but we'll come to that later. So firstly, let me explain this stuff. Now, what is h hat? That's important. So h hat is so it's minus 1 upon 2m p hat squared uh, plus the potential. So once again, what's p hat now? So p hat is this thing, h hat, so h bar upon iota, obviously, you know that thing, the imaginary unit. Why am I even explaining this? So partial upon partial x. Yeah, so this is an operator. So now p hat square is not like apply p hat on psi and then square it. No, it means apply p hat twice. So p hat square is basically like h bar upon I partial x and h bar upon I partial x, which just becomes negative h bar square by partial x square. So essentially what you're saying is that I h bar partial psi by partial t, that's equal to so just p hat square upon 2m. So this should not be negative over there, right? So just p hat square upon 2m, right, which is happens to be minus h bar squared upon 2m partial square by partial x square, and the psi thing obviously, and plus v times of psi. So this is not an operator, this is just the potential. So what is psi a function of? Psi is mainly a function of obviously time. Everything's a function of time, by the way, and it's a function of the position. So for now we're just thinking of it as a one-dimensional wave function, but will generalize soon. So psi of xt basically, and the potential is also a function of x and t, but in most cases we'll just think of it as a function of x. That is that the potential is not dependent on time. So now with this explained, we can go to the next thing. First, like let's just get familiar with what all of this even does. So we are going to go to the most basic quantum mechanical system one could ever imagine, which is just a square well, right? So this is a one-dimensional well basically, and the way this works is that, so you have this x-axis, and this is x equal to 0, this is x equal to some a quantity, and everything over here is inaccessible, which is given by basically the voltage, the potential being equal to infinity. Over here everything's equally accessible, so that's potential equal to 0, or you could choose anything really, but we're just going to go with 0, and this is v equal to infinity again. So yeah, now another important thing that I sort of forgot to mention was that what does this wave function even represent? Well, it's sort of at this point common knowledge, because this is just spread everywhere on the internet. But the magnitude of psi square, this is the probability density function with respect to x. So this is basically like if I multiply this by dx, and this is the probability that your x is between x and x plus dx. This was weird to say, but I think you get what I'm trying to say, right? because most of you probably have dealt with probability, statistics, all of that stuff. Anyway, so the infinite square well is a classic example, and it's kind of easy to solve. So you have this wave function thing. So that's Schrodinger equation. I'm just going to copy this stuff. So now let's try to solve this, and we're going to solve this by, well, the most let's just say overused method, which is separation of variables. But like, this is really just the only method that you kind of need to apply. So what we're essentially going to say is that if you can find some solutions, then every linear combination of that solution is also a solution, right? So we'll try to find some solutions of a particular form, and that particular form will be that your psi will basically be, so it's a function of x and t, right? Now I'm thinking of it as a function of x first and then some other function of time. And so putting that into this equation, what you essentially get is so I h bar, and then this stuff, it just gives us this, and that's minus h bar upon, so h bar square upon 2m, and then this just gives us this plus so v is just 0. Like in this whole area, v is 0, and over here, like, you don't kind of care about this. So since this quantity is the probability density function, and we kind of require continuity in physical space, like the probability of density function over here and over here, they should almost be the same, right? So what we are going to say, and we know that it can't be here, like, yeah, this from this point onwards, the probability of it being in this space, that's just 0. So by sort of continuing, we can say that over here it's also 0. So then our curve for psi squared, the magnitude of psi squared, would look something like this. I kind of don't know what it's going to look like, but it's going to be 0 over here and over here, right? Okay. So any solution to this boundary condition at the same time to the wave equation, right? If we can find some such solutions, well, we can just combine these solutions, and that's going to be a general solution, right? Okay. So, like, yeah, first we'll just have to solve this thing. Now what I can do is I can separate this, so it just becomes so that, like, h bar, yes, okay. So I can divide this, and then we'll just have I h bar f dash upon f, that's equal to negative h bar squared upon 2m, and then psi double dash upon psi, and I'm gonna set this equal to some energy E, right? So now solving, so why did I do this? So E is not necessarily the energy, it's just something, but notice that this is a function of time only, and this is a function of position only, and so that means this has to be a constant, because it can't be a position of x or t, it has to be like a function of both, and the only thing that does that is a constant, right? So sorry, a function of none is more like it, but if that makes any sense. Anyway, like, yeah, like, this is independent of x and independent of time, so the only way this could be happening is if it's a constant. So now this is some constant, we're going to solve some stuff with it. So first let's solve this stuff. So it just gives us f dash equal to so actually not f dash, I'm just gonna, like, directly write the solution. So it's just e power minus, sorry, yeah, okay, right, minus I e upon h bar, basically, times t, obviously, right? Like, differentiate it, what do you get? Minus iota e upon h bar, and then the same stuff, right? So f dash equal to minus iota upon h bar, and then f. So yeah, this satisfies the equation. Now it should probably be having a constant in front of that, right? That's what you're thinking. Ignore it. Just completely ignore that, and the reason for that is, well, you can just have that constant inside of the psi thing, this small psi thing, right? Because it's multiplication in the end. So yeah, and it's just a constant, so put that inside. Anyway, we're going to solve this now, and let's see what we get. So you just have psi double dash is equal to, so what's this thing, minus 2m upon h bar squared e psi. So this is basically like SHM, right? You remember the very basic equation that you have, like d square x upon dt square is equal to minus kx and all that stuff, right? It's just that. So what's the solution of this thing? Well, its psi is equal to some sinusoidal function. So like a sine of omega is just the square root of this quantity. In this case, that quantity is just 2me upon h bar, so it's going to be like square root of 2me upon h bar, if that makes any sense. Right, so omega, right, x, yeah, plus some phi, that which is like some phase constant, I don't know. Right, so once again, omega is the square root of 2me upon h bar, right? Cool. But now that we have this thing, size, all that stuff, we can use the boundary conditions and then say, okay, psi has to be necessarily 0, because at x equal to 0, you require the wave function to be like gone, basically. But also, what should happen is that omega x, that should be equal to, so omega a, basically, that should be equal to n pi, n is some integer, so that it's also 0 at this position, right? Now omega is this stuff, obviously, so you have square root of 2me upon h bar a, that's equal to n pi, and from that you get some nice things. So yeah, you just get 2me is equal to n square pi square upon a square h bar square, which means that energy is quantized. It can only take some certain values, and that's going to be the theme throughout. So this is like a very basic sort of toy example. Like, you are never actually going to see anything like an infinite square well. Like, this is too simplistic, and it's also unrealistic. But this is as a good starting point. So upon a square and 2m. Yes, I'm eating something. Don't mind that. So energy is this thing. So that was pretty easy, right? So it's n square, pi square, h bar square, all that stuff. What we're basically saying is that energy can only take these values, nothing else. Okay, that's cool. But then again, this isn't the solution. It's just one of the solutions. You could have many such solutions. The full solution is basically given by, well, so n is some integer, right? Let's just choose it to be something, let's say 1 or 2 or something like that. Then let's say you choose it to be 0. You would be getting something like some solution corresponding to that, psi sub n, right? So this is the time independent part, and then you also have some time dependent part, because energy is there, and so it's depending on time and all, right? So this is like one of your solutions. But then you also have some other thing, right? So maybe like, so this was maybe n equal to 1 or n equal to 0, or who knows, whatever, and then so on. So all of these are valid solutions. So the general solution in that case would be something like this. It would be the summation c sub n of psi sub n, f sub n, right? And this is from n equal to 0 to infinity, because like we can do that. Yeah, right, like it, yeah. What was I going to say? Yeah, so it doesn't actually matter if n is positive or negative. So like we can just choose to be, for it to be non-negative, and there you go, you're gonna have the thing, because n square, right? So it doesn't really matter. So that's your like total wave function, which is like the wave function. Now there's like important thing that I'm going to say. What we just did is basically find the eigenvalues of an operator, which is the Hamiltonian okay, this is a bit too complex for you right now, I think. But yeah, so what we have just done is figured out a decomposition of any wave function as a solution to the equation into a bunch of functions which we got by solving some differential equation, right? And these functions are specific, like these sort of functions are going to come everywhere throughout quantum mechanics, and these coefficients over there, they also have a special place. So one thing you know is that since it's a probability distribution, what should happen is that the integration of psi square this should be equal to 1, but then that immediately implies that the summation, so these by the way are also, like, we can just normalize them, right? So without loss of generality, assume that these are also normalized, as in the integration of these guys is also 1, so just assume that. Then you can say that summation from n equal to 0 to infinity, and this is by the way magnitude 1, like you know that because it's just a complex exponential. So then from n equal to 0 to infinity of these coefficients square magnitude obviously, that thing is equal to 1. This is just math, you can prove that, I'm sure of this. It has to do with the orthogonality of these sort of functions, right? Yeah. So just do this stuff, and what you'll see is that this happens, like this thing holds true. And so from that we can sort of get an idea as to what these Cn things represent, at least what this thing represents. This can be interpreted as the probability of the energy, basically, of the energy being in what do we call it, in the nth state, basically. So the nth state has the wave function as this quantity. Well, that's multiplied by something. That something is basically the probability of your energy being E sub n, right? And so now that I've motivated this thing, let's get into like the basics of quantum mechanics, right? So this was just sort of a prologue, if you will. This really isn't quantum mechanics, but let's get into it. So wave function interpretation, I guess you already know, right? That so if you have a wave function which is not normalized, well, normalize that, right? So sometimes you just get solutions which are not normalized. In that case, normalize the solutions, and then that wave function is going to represent the probability distribution, well, the square of that, at least the magnitude square. Yes. So now let's finally get to something called operators. So so let's say I gave you the wave function, and I want you to figure out the position, the expected value of the position of your particle, right? So psi square is just the probability distribution function for the position, right? So what is the expected value of the position? Well, that's just this quantity, right? But then you can write it slightly differently. You can write it as psi star x psi dx, right? And then in fact, if I want you to figure out the position, so what momentum is, like the expected value, how are you actually going to do that, right? That's like a hard task, because you don't have any meaningful way of defining the momentum like at an instant, right? The moment you make an observation. So how do you know, like, can you actually get from psi the momentum exactly? No, you can't. But what you can get is the derivative of the expected value of x. And so the d by dt x thing, I'm just gonna say that that is the momentum, the expected value of it. Yes, this is sort of not good, but that's the best we can do. So I'm just gonna move with it. And the more formalism we build up, the more postulates we have, the better will everything be. But for now, this is like what you have to deal with. So we're just going to figure out what this quantity is. So it's just the derivative of this thing. So the derivative of this thing is basically like, so you can use the product rule over there, and what you will have is something like d by dt of psi star x psi dx plus integration d by dt of plus integration of psi star x d by dt psi dx, and something like that, right? So one thing to note is that the derivative of psi square, right, that thing isn't like all that straightforward to calculate, but okay, let's actually try to do this thing. So okay, how do we do this? What we'll have to do is basically like use the Schrodinger equation once again. So you know that in the Schrodinger equation there was this d by dt term, right? You just had I h bar partial psi upon partial t is equal to h hat psi, right? Yes. So now what we can do is take the conjugate of this whole thing. So we'll just have IH partial psi star upon partial t is equal to h bar psi star. Yes, this is a completely okay. H bar h hat star. That's a kind of what I should be saying. So this is how it's going to be. So now h hat doesn't really have any iotas or anything, right? Like h hat is just this quantity. So h hat star is basically h hat, and so this just becomes this, right? But over here you should actually have a negative. So you took the conjugate of the whole thing, right? Of the whole equation, not just psi. Like that's not valid to do. You can't just take the conjugate of one part and say, oh, we are done. No, that's wrong. Okay. So now we're going to use this thing. We can subtract this out. Right. And so now what we kind of need is the derivative of the magnitude of psi squared, right? That's what we need over here. So the way that happens is you think of this quantity as being psi star psi. And so just as I did before, you do this thing, psi star d by dt of psi plus d by dt of psi star and then psi, right? But now you know what these quantities are from this thing. And so you combine all of that, and then essentially what you get after doing all of this is that this quantity, you can write it like this. You can write the expected value of the momentum, or more like the momentum of the expected value of the position. I don't know if that makes any sense. Oh, by the way, this is not the correct equation. This is the correct equation, just so you know. But like, yeah, you get that. So that thing is just integration of psi star h hat, so h bar upon I partial x of psi dx. So now if you recall, this thing is called something. This is the momentum operator. So is it, so like, yeah, by the way, this equation just verified for yourself, but it does happen. So just have psi star p hat psi and dx, right? And there you go. This is the this is like the basic rule that whatever observable you have, the expected value of that is just given as psi star, whatever corresponding operator you have for the observable, psi and then dx. So this operator acts on psi, and then you do psi star and then that, right? So now this whole thing can be put into some really nice like linear algebra using, well, thinking of each function as a vector basically. And so what people do is that we write it like this. We write it as psi operator and then psi, right? Or sometimes they write it like this. So this thing is called a ket, and it sort of represents a vector. Like, not exactly, okay, yeah, it represents a vector, but not finite dimensional vectors. It represents things in vector spaces, and these things can be infinite dimensional, like functions, right? So functions are arguably vectors, right? So is psi. Psi is a function, and thus it can be thought of as a vector because it satisfies the the rules of vector addition and all that, right? So this operator acts on this vector, which is the ket psi thing, and then this stuff, this is called a BRA. No, this is not the clothing thing that people that ladies wear. No, this is like a notation that somebody came up with, and essentially what we're doing is that we're taking a dot product. So what we do when we say BRA, so the applied on some vector, which is like some ket B vector, what we are saying is that if you sort of write this in normal notation like A vector and B vector, then this thing is just A vector transpose, but then the conjugate of that. And so that applied on B vector, obviously. That's what we're doing. So essentially we're just taking the conjugate of A and then taking a dot product of that with B. But in this particular case, it's slightly different because we're dealing with continuous space. So it's a function space, right? So we have infinite dimensional vectors, and so dot product does not make sense directly. And so instead what this bra thing does is that it does this operation like integration of a and then so a star basically, and then b and dx, something like that. So if a and b are like functions, right, then this what this that's what this thing does. Yeah, so I kind of don't want this, right? And so this thing that we just did, this is called the inner product. It's the inner product between the function psi and the function that you'll get after applying operator O hat to psi. So O hat psi is some function, whatever, of x and t. And so you're taking an inner product between these two functions, right? Yeah. And so this is the basic fundamental rule. Also, by the way, from this inner product you can get the notion of a norm as well. Like the norm then is just given as the square root of the inner product, so the product or whatever inner product of some function with itself, right? Yeah. But anyway, coming back to quantum mechanics, we are finally to the sort of second most important postulate in quantum mechanics, which is observables and their probability. So every observable can be thought of as an operator. So a Hamiltonian, which is basically the total energy of the system, that is an observable, but now that can also be thought of as an operator h hat, right? You saw the form of that already, right? Yeah, and so now you are going to not think of psi as just a function, but rather something in a function space. And so instead of writing it as this thing, I'm going to write it slightly differently. I'm going to write it as an eigenstate, a heavy word really, but I'm going to write it as a vector basically. Eigenstates are going to come later actually. And what we'll say is that so for any operator O hat, so you have an observable O, from that you get an operator O hat, and you do it like this. So for example, if you wanted to find the what we call it, the operator for this observable p cube upon something x, not x, okay, upon a, some constant, then what you would do is just replace p by p hat everywhere, and that would be the operator corresponding to this observable. And so every observable will basically be a function of x and p, right? So what you have to do is just replace x by, well, itself, so just get some f of x, but p with p hat, and that will be your operator basically. Okay, so now let's go to the main thing, which is the eigenvalues of these operators. So what you saw for the time independent part of the wave function, the psi thing that I was writing, was that for some energy, basically what you wrote is like h hat of psi is equal to energy. Just go back and see that that's happening, like this is the equation. So whatever E constant that you chose, you can write h hat psi equal to E, and this is like more general really, like, okay, I'm gonna do this in fact. So I h bar partial psi by partial t. So assuming that the v thing is not a function of time, what you can say is that this h hat thing is also not a function. Okay, this is a kind of weird. Operator is not a function, but you get it right. That this does not involve time, right? And so if I think of the psi thing as just some psi of x times some f of t, then what we'll essentially get is I h hat, so I h hat psi f dash is equal to so this is just the part which this h hat is actually going to be applied on, and so this actually just comes on the front. But now you can divide by psi and you just get I h bar f dash upon f is equal to, and so this is actually what we set to E, right? And so from this equation what you actually have is like h hat psi that's equal to E psi. And so this is the basic equation for the time independent part of the wave equation, which you're gonna get like all the time, and the infinite square was like just one example. But anyway, um, yeah. So what you notice is that what's basically happening is that like for any solution, you have any separable solution, right? So this form, like you can write psi as, you know, some time independent part and time dependent part. This is called the separation of variables. So a solution like that is a separable solution. So for any separable solution, what you can sort of say is that h hat, some operator applied on the wave function, the solution basically, that gives the energy which is some value, and that times of psi. So now we're thinking of psi as not just a function but rather as a vector, right? And so the equation that you're going to write is something like this. And for anybody who has studied a bit of linear algebra, what you realize is that this is an eigenvalue equation basically. Like h hat is some matrix, you can think of it like that, although not exactly. Like infinite dimensional matrix is sort of are scary, but it's some linear transformation, right? And yes, it is a linear transformation. Check that out for yourself. It like gets some vector, it outputs some other vector anyway. So h hat of psi, that's equal to E of psi. So that just means that E is an eigenvalue of h hat, and this thing get psi, that's an eigenvector for this corresponding eigenvalue. So now an important thing is that every operator is basically going to be Hermitian, which is something, just search that up. What it basically is that you know, if you like whatever operator you have, if it's a Hermitian operator, then it's something like this. That's an Hermitian operator, but like never mind all that. Okay, so where was I? Yeah, so for any operator, in fact, you can sort of extend this. Like for any operator, for every separable solution, what you will have is that so I shouldn't say the separable solution, okay, whatever. So for every eigenvector, right? So for every eigenvector of this operator, you're obviously going to get some sort of eigenvalue, right? So lambda, let's just call this sub lambda. Yeah. So you will have an equation like this. Now these lambda values are precisely the values of the observable corresponding to this operator. As in whatever observable O you had, the values that O can take, that's lambda. So for example, the values that h hat could take for this particular Hamiltonian that we had, that were, well, the solutions for the energies in the infinite square wave, right? Yeah, but in general, whatever operator you have, the eigen values of that are basically the values that you can take, and that's sort of the postulate that I'm going for. For any observable, you get its operator by doing some stuff which I've described already. Then every eigenstate of the operator with an eigenvalue lambda is one of the values that O can take, right? So O can be lambda 1, lambda 2, lambda whatever, right? And if you can write the solution, like the actual solution to the Schrodinger equation, so O is not necessarily the Hamiltonian operator, it's any operator really. So for any operator you can do this, right? So whatever solution that you get for the Schrodinger equation, if you can express that using these eigen vectors, right, as something like this, summation of p sub lambda so if you can express it like that, then what you actually are going to have is that this quantity is the probability that O is lambda, right? And that's the postulate. That's like one of the more like the other important postulate of quantum mechanics. Right, so that's observables and their probability. Now let's go to the uncertainty principle. Yes, this is actually an interesting part. Right, so first we need to understand how do we calculate standard deviations of stuff. So standard deviation can be calculated like this thing. For any observable O, your variance in O, that's this quantity. Like whatever solution that you're going to get, for that particular solution, your standard deviation will be given, right? Yeah. So it's O hat minus O squared psi. Yep. Which is, by the way, just this. So what does this like mean? We're just going to apply this new operator of O hat minus O. Yeah. Right. How do I say this thing though? I kind of don't know. I think this definition is not the one that we should be going for. Yeah, okay, let's not go with this definition. Let's go to the other one. So it's basically like the expected value of whatever operator we have squared minus this quantity, right? Yeah. So this you can get by doing this thing. Right, and this you can get by doing this thing. Right. And so what the uncertainty principle says is that for any observables A and B, first you calculate this quantity, which is called the, so first you calculate their operators, obviously A hat, B hat. Then you calculate this quantity, which is called the commutator of A and B, and that's given by this thing, A hat, B hat. So it's an operator, by the way, minus B hat, A hat. And some lucky times what happens is that this thing just turns out to be a constant, right? Multiplication with a constant, to be more specific. It's an operation in the end. But then what you do is you calculate this thing, yes, I know that's a lot of steps really, but you calculate whatever this quantity is. You take the magnitude of this thing, right? So this is an operator, and I think at this point you know what we are doing over here, right? And so what the uncertainty principle says is that the standard deviation, so you have the variance divide, so just take the square root, and that should give you the standard deviation really. So the standard deviation of the first observable and the standard deviation of the second observable, multiply them, that's bigger than or equal to this thing. So this is proved by Cauchy-Schwarz and other stuff, but yeah, you can like sort of try to do this thing. Okay. Yeah. Okay, next. Right. Okay, so now let's sort of get into like an understanding as to why this principle matters so much and what this operation is and why does that matter. So here's another sort of principle in quantum mechanics. If you have two operators A and B, A hat and B hat, sorry, and they have the same, so they have a complete set of eigenvectors, and what that means is that whatever solution that you're going to have in like solving the Schrodinger equation, whatever solution you're going to get, that solution can be representable completely using the eigen vectors of the operators, right? Or more like the shared eigenvectors of the operator. So if they have a complete set of shared eigenvectors, then their commutator is going to be 0 basically, and that's trivial to prove, and this is more or less an if and only if condition. So if they share the, so have complete set of eigenvectors, that is the same as saying that the commutator is 0, right? The zero operator basically. Yeah. And so what was I going to say though? Right. Yeah, so why is this so important? So what this means, the first thing, what that means is actually profound. So if the eigenvectors are, I mean, you have a complete set of eigenvectors, then what that means is that any psi can be written in those like eigenvectors. So even the eigenvectors that are not sort of in that set, they can be written like that, which is to say that like there's some weird stuff going on, but never mind. The basic thing is that the set of eigenvectors that these guys share, which is complete, it can be used to write everything, every single every single psi that you're going to get, you can write it using that. Okay, but now we can rely on this postulate and say that, well, whatever psi you had, you can express it, right? You can express it as so using the eigenvectors, it's like summation of c sub lambda, summation of p sub lambda right. So you do that thing, yeah, and you know that the probability of, well, let's just like think about one operator for now. So the probability of a being lambda is exactly this thing, right? Okay, well, since you expressed it like that, and these are also the eigenvectors of b, yeah, so you sort of did something. So they don't have the same eigenvalues though, like although they are the same eigenvectors, they don't have the same eigenvalues. Like this might have value lambda for a and value mu for b or something like that, I don't know, right? So but what we're going for is that, like, so p lambda, that's just the probability of well, a having some value lambda, right? And let's just say that for this the corresponding value is mu or something for b, right, the eigenvalue. Then p lambda square is also the probability for b having the value mu. Moreover, both of these events happen at the same time, and so this eigenvector represents a pair of values, one for a and one for b, and both of these are simultaneously going to happen. Like if a gets the value lambda, then b must get the value of mu, right? Yeah, and that's like whenever this situation happens, that knowing the value of a completely determines the value of b, this is called compatible operators, as in we can find the values of a and b at the same time without any uncertainty. But if this is not equal to 0, right, in that case we cannot do that, because what you're going to get is so what basically I should be saying instead of this is that if you just had this thing, like one particular eigenstate, right? So if your psi was just one particular eigenstate, right, that's the solution, then we know that it has some corresponding lambda value and mu value, right? So a would just be equal to this thing, b would just be equal to that thing, right? Yeah, but now if these were incompatible, and yeah, you had psi equal to the eigenstate psi sub lambda, right, then yes, a would certainly be this thing, but b will not be this, because there is no such one particular mu, right? Remember that this is now not an eigenvector of b, like possibly not an eigenvector, which means that you will have to express this as summation of c sub mu, sorry, p sub mu, right, psi sub mu, right? And then these will be the probabilities of b being those values. Yeah. So now, moreover, like the standard deviation of this thing is 0, so this kind of probability has to skyrocket like to infinity or something. But yeah, this stuff happens, right? And so that's what the uncertainty principle sort of encodes, that if you're like the two operators are incompatible, right, then you cannot know one while also completely knowing the other one, right? You will have some probability of b having two different or three different values given a, and that's an issue sometimes, because to represent a state of your system, you want to be able to write down every single property it has, right? So if you do this for observables which are incompatible, you cannot write this. Like, you know what this first value is, you do not know what the second value is at that point, right? Yeah, so this is like what the uncertainty principle really is at its basics. It is not something like, oh, you know what position is, you not know what the momentum is, like that. That's okay, that's one thing, that's the Heisenberg uncertainty principle, which is just a special case of this thing. But this is the more general scenario, and the reason to that is, the reason like this happens is actually very basic. But yeah, moving on to the Heisenberg uncertainty principle. So for our position and momentum operator, so by the way, the position operator is just the position itself, right? Okay, the momentum operator is, well, you know what this thing is. So for the position and momentum operator, the commutator is basically, the commutator is given by this thing. It's iota h bar. But now plugging this stuff into the into the uncertainty principle, the general one, obviously, what you're going to get is that sigma x, sigma p, the standard deviations in x and p, that's bigger than or equal to, so this multiplication is bigger than or equal to h bar upon 2, right? So this is commonly also written as delta x, delta p bigger than or equal to h upon 4 pi. And we say that delta x is the uncertainty and delta p is the, so delta x is the uncertainty in position, this is the uncertainty in the momentum. What we should be saying is this is the standard deviation of the distribution or something like that. Okay, so this is sort of the basic thing in quantum mechanics. Now I kind of want to be doing the simple harmonic oscillator in quantum mechanics, but like I figure out, I think this will just be a bit too basic, right? Like, yes, you have some stuff which is sort of non-trivial, like you're going to get an integration rather than a summation now, or something like that. But yeah, sorry, wait, no, okay, so you're still going to get a summation. It's the free particle which gives you an integration, but yeah, but still it's sort of basic actually. So I think we are not going to do that. So instead, let's go to something slightly more complicated, which is angular momentum, right? So the angular momentum is given as r vector cross p vector, right? In classical mechanics, and so you can write it as this thing, rx, ry, rz, cross that with px, py, pz, and like everybody knows how to like calculate this stuff. So this just gives us ry pz minus rz py, and rz px minus pz rx or something. I should be writing x pz because like it's important what order you have, right? Yeah, okay. And also for the z component, just have this thing, so rx py minus ry px or something like that, right? I mean, it is obviously that, come on, cross product. So that's the angular momentum. Now, like, if I just write one of the components like ry p sub z minus r sub z p sub y, right? Like, this is just classical mechanics. But what if I want to go to quantum mechanics now? What I'll have to do is write it as an operator. So this will be, well, this is basically the y coordinate, so just y hat is just y itself. Now the z position, so the z momentum, that has this operator h bar upon I partial z, right? Minus this is just the z coordinate, and then partial h bar upon I partial y, right? So that's the x angular momentum operator, right? And similarly you get some other operators and whatever. Now with these operators you write the commutator relation, right? Yeah, and with that commutator relation you start solving stuff like you figure out the eigenvalues of the angular momentum operators, right? Yeah, and actually there's like quite a bit of good math in this. Like there's this stuff that L squared operator is like compatible with Lz and all that stuff, like this is equal to 0, and then you'll have these ladder operations, L plus is equal to Lx plus iota Ly and all that stuff. So all the sweet stuff you do, and what you'll basically get is that what was I going to say? I kind of forgot. Yeah, I kind of forgot that one. Yeah, so the angle, right. I was going to say this thing. So the angular momentum can, so it has these eigenvalues like L square. This operator has the eigenvalues of h bar square times L plus 1, where this number is very familiar because it's the quantum number that comes in a lot of basic chemistry courses. Yes, this is the number for angular momentum, the orbital angular momentum to be more specific. Yeah, and you will also have Lz having some value like just h bar m basically, right? Yes, so basically like m will be like in some certain values only. It's gonna be like negative L minus L plus 1 and so on till 0, and then so on like till L basically. These are the only values that m can take because of this fact that L sub z square is less than or equal to L square, right? But yeah, and like how do I say this thing? Yes, so like L square, this is kind of complicated to be saying, isn't it? Yeah. Oh god. But never mind all that. Okay, cool. So now what I'm going to do is sort of like extend this thing into the spin angular momentum. So this is still dealing with the position wave function psi, right? Next, what we are going to be doing is deal with the spin wave function, which is something that is, I still don't know how to wrap my head around that. Like it still looks weird and bizarre to me, but the mathematics of that is basically carbon copy of the mathematics for orbital angular momentum, right? And so you have these operators. Okay, so I'm gonna start with like the most basic thing, that the eigenstate that's given as, so it's given by just in this case the orbital angular momentum, it's given by L and M, right? You specify what L and M is, you specify the whole function, basically the wave function. So now since it's a carbon copy of just that, now your eigenstate is going to be given as S and M, and it just so happens that S can only have one value, namely half. So if S is only half, then M can only be negative half, because like starting with negative L, now it's going to start with negative S instead, and then that plus 1, so just half, right? Yeah, because now that is actually just equal to S itself, so it's got to stop there. And so what I'm going to do is like forget about this M thing and just write it as get S. So S is like a number basically, it's like half or minus half. So these states are basically the only states that your spin angular momentum can be in. And so from that you have something called a spinor, and this represents the distribution of your wave function into the two eigen states possible. So that it's given by basically just a vector, a 2 vector, like pretty easy, just a and b, some numbers. So what this represents is that it's a so it's like probability a, so it has part A of this and part B of that. So it's, if I just wrote that your wave function is this thing, then what that actually kind of means, I should be writing this thing. It means that I'm actually writing this thing, right? So this is basically it's related to qubits and stuff, and it's like gonna come in quantum computing apparently. But anyway, now let's go to the operators, because okay, so because we said that these are, so L square and Z are like I told you that they are compatible, right? So now similarly you have S square and SZ as the two compatible operators, and also with these you also have these operators which are also compatible, S plus and S sorry, actually these are not compatible with them, sorry. So you just have these operators, S plus, S minus, Sx and Sy, and these are, all of these in fact are not compatible with these. But anyway, S square in this case is just given as this matrix 1 0 0 1, and then you just have 3 upon 4 h bar square. So remember what I told you, right? That this will be your L square value, h bar squared L times L plus 1. In this case, instead of L you have S times S plus 1, but then S is just minus half or half, right? So if it's half, then it's like 3 by 4 h bar square or something. If it's minus half, then it's like, so it's still the same actually. Wait, is it? No, it's not. Okay, it's actually this thing. It's minus 3 by 4 h bar square, right? Wait, I guess messed up somewhere. I don't know. Okay, no, wait, this is not that. So if it's negative half, then it's like h bar squared, and then oh, so it is actually just going to be h. So yeah, I remember that. So it's actually not. So this S thing that I wrote is a different S thing now. It was SM, right? You remember that? So this M thing is actually what's variable. S was just one fixed value. So instead of L, you gotta write S, but then S is half all the time. So it's just this thing. It's just 3 by 4 h bar squared, right? And so your S square operator is basically this thing, and it like acts on AB. It gives precisely 3 by 4 h bar square AB back. So yeah, this is an eigenvalue, pretty obvious. Now SZ is slightly different. SZ is this thing, h bar, and then 1 0 0 minus 1. So you remember that in the angular momentum case it was like h bar m, that's the, so it's h bar upon 2, sorry, h bar m. So you know that was the eigenvalue, right? Over here as well, this is the eigenvalue. So if your m is 1, that is to say you have state sorry, if your m is half, it is to say you have state half, then it's like 1 0 basically. That's a spinor. You put that in, and then the eigenvalue you get is like obviously just h bar upon 2. But then if it's the other state, and there are like just two states basically, so you put that and you get minus h bar by 2. So this was m equal to negative half case, right? Yeah. So this is consistent with what was happening in the angular momentum case. So far you have considered S square and SZ. Now we're going to go to the S plus and S minus cases. So these are called ladder operations. And okay, I should have done the harmonic oscillator first, because then you would have understood what ladder operations really are. But I don't think we have time for that at this point. But what the ladder operations do is that given an eigenstate, they give you some other eigenstate which has a different value of the observable, right? And so the two ladder operations that we have for angular momentum and also for orbital angular momentum and for spin angular momentum are the plus and minus operators. So S plus is just Sx plus iota Sy, and then S minus is just Sx minus iota Sy, and these are given by these matrices. So what S plus does is that if it's in the negative half state, it sends it to the half state, right? So it's basically this thing, 0 0 1 0, and this thing is 0 1. So it's gonna do exactly the opposite. If it's in the positive half, it sends it to the negative half. Also, like if you are in the positive half state, then S plus will send you to 0, and that's an important thing actually, which you will understand when you read the text. So I've just read this introductory text on quantum mechanics by Griffiths, Go read that if you want to get like used to this stuff. Right, so s minus is just this quantity, and so from that it's very easy, like sx you can easily figure out, it's just half of 0 0 1 1, right? And then sy is just subtract that, negative iota times that, so it's just 0 negative iota, and this thing is minus 1 times minus 1, so it's like iota. Yes, so that's sy. And so these are called Pauli matrices, because some guy named Pauli discovered them. Anyway, so that was spin, angular momentum, and stuff. Yeah, and I guess this is where we should stop with the basic quantum mechanics. And so the next video I'm gonna make is about phonons and stuff. So it's like about you know vibrations in what in materials which are isotropic, which is like sort of unrelated to this, but it all like really neatly combines into quantum statistical mechanics, which I am reading right now. So yeah, I guess this is pretty much it. And yes, I have I have like latex type proper notes on this stuff, which I'll actually link in the description. So if you are eager to learn all of this, go through that. Like it's just some basics, not much over there, but I think what I personally believe is that, at least for me, they were like those notes are better than what Griffiths has, because it says like Griffiths has a lot of exercises and examples everywhere, and which is like completely nice, good. But if you just want to go through it and like not put too much stress on your head, go through my notes. I prefer those. Alright then, so I'll see you guys in the next video. Bye.